Welcome to Validated. We're back. We're doing something a little bit different today. So, as many of you may know, I left the Solana Foundation at the beginning of December to work on a new project called DoubleZero. I'm joined here today with Andrew McConnell and Mateo Ward, my two co-founders in this new endeavor, and we're going to talk a little bit about DoubleZero, the state of the internet, high-performance networking, and a lot of its applications for blockchains and high-performance distributed systems. Mateo, Andrew, welcome.
Thanks, Austin. Happy to be here. Excited.
Thanks, Austin.
All right. So before we dive into what DoubleZero is, I think it's useful to kind of start with both of your backgrounds because neither of you come from a traditionally crypto background.
Yeah, absolutely. Actually, Andrew and I have very parallel backgrounds, and so we thought we'd kind of go back and forth with each phase. Andrew had an internet phase just like me at the beginning. Then he moved on to exchanges, and I moved on to telco carriers. And then we both finished up building high-performance networks for distributed systems. So, just starting out on my side, after doing some mobile networking, I really got into subsea fiber networks at Global Crossing, building the first global subsea network that was private and optimized for latency and best route all over the world. And that ended up being one of the backbones of the internet, one of the underlying infrastructure pieces of the internet. And during that time, Andrew was actually working at a global ISP.
Yeah, that's right. So I started my career at SunGuard Availability Services in Philadelphia, building out a managed hosting services business back when enterprises were just sort of dipping their feet into Web 1 style hosting infrastructures, putting up electronic storefronts. And part of that was, running effectively an ISP. So we had servers that were connected to switches that were then connected to the global internet. We had points of presence all over the United States and London. So I sort of got my start loving the internet and engineering the systems behind it.
Excellent. And then right after my internet phase, I got into telco carriers. I was the founder and CEO of a carrier for 10 years. And telecom carriers are the backbone of the internet as well. They peer together and they create the connections that our traffic runs over. And we're going to talk a lot more about that in a few minutes. But that was a fascinating part of my career. It's when I got into software-defined networks, very applicable to what we're doing here. And then also ultra-low latency terrestrial networks to complement the subsea networks. While I was doing that, Andrew was getting into stock exchange infrastructure.
Yeah, right. So internet engineering is interesting. There's quite a lot of aspects to it, but it turns into a cookie cutter engineering design over time. So you're solving the same problem over and over again. How do I get enough bandwidth to this customer and then do that wash, rinse, repeat? So I followed one of my colleagues over to the Philadelphia Stock Exchange just down the road, where the problem solving was much more interesting in fintech. So instead of just thinking about bandwidth for customers, you were thinking about the throughput and latency needs of running a profitable exchange. So this sort of reopened my eyes and energy into network engineering, because instead of just creating connectivity, it was the first time that I was really thinking about how do you create good connectivity, high quality connectivity that actually matters. It's more about the performance than just pure reachability.
After that phase of telco, I got into high performance networking full time, and that's really been the most exciting phase of my career. Working with software-defined networks, building carrier-to-carrier interconnects and optimizing traffic flows, and also building infrastructure for finance. Finance infrastructure is probably the most performant infrastructure in the world, the lowest latency, and the applications that run on it are very time sensitive and need high-performance networks. So we sold the carrier that I was running back in 2020, and I spent sort of the last 3 years working on these ultra low latency networks, building shortwave networks that beam signals through the ionosphere between continents for ultra low latency applications, as well as co-founding a cybersecurity company called Invito and getting really into cybersecurity, which, as you all know, is a critical part of running a global distributed network, keeping it secure. And during that time, Andrew moved into HFT world as well.
Yeah, that's right. After the Philadelphia Stock Exchange was acquired by NASDAQ, I hung around for a bit, and it sort of felt, to me anyway, at the time, like going from the minor leagues to the major leagues. Sort of the U.S. equities market was where performance was really starting to matter towards the sort of 2008, 2009 timeframe. But I also, once again, realized that there was even more interesting stuff happening on the participant side of the exchange than at the exchange itself. So while the exchange had to build some high performance networks to take in orders and to distribute market data to the participants, a much more appealing, at least to me, problem set was how to understand how all the exchanges all over the world operate and how they build their networks, and sort of build a trading system tailor-made to trade on each of those exchanges. So I moved out to Chicago, joined the high-frequency trading community, and then I spent the next 15 years building out the craziest sort of purpose-built, bespoke networks that you can possibly imagine. I'll never forget the moment that my manager explained to me that we were going to build a network from Chicago to New York wirelessly, and I was like, "Oh, who's going to do that?" And they're like, "You." That's the sort of style of networking that I found myself getting into, and enjoy that type of problem space.
I think the second part of your question is like, how did we end up here? I'd like us all three to answer that, because we're kind of doing this together. But I've always been interested in building networks for emerging technology, and really my role here in the project and in Malbec Labs is as a business technologist. Andrew's running engineering and getting deep into the technology stack, but my role is finding out where the value lies in the intersection of technology and business. And that's what I've done my whole career. And once you find out where that point of value is, I've specialized in building projects and companies around that and scaling them. And so back in summer of 2016, I'd gotten deep into low latency networking, as I said, and I was in Chicago, walking to the subway with one of my investors to go to a baseball game. And he said, "Hey, we're going to get into crypto." And I said, "Wow, that's great. Another emerging tech thing for me to build underlying high performance networks for." And he said, "No, it's too early. Crypto is dispersed. Crypto lives in the cloud. It lives on the internet. You can't see the traffic. You can't optimize it." And I was very frustrated. And I said, "Well, someday we'll be able to do this."
When was this?
This was back in 2016, right when a lot of the larger trading firms, hedge funds, and people started getting into crypto trading. But the network was not developed, and the traffic patterns weren't developed. So by 2018, though, things had started to change. There were centralized crypto exchanges, and I was part of the very first project at one of these large financial firms to build an optimized network to a centralized trading exchange in Dublin. The exchange was in AWS Europe West 1 region in Dublin. And we had to build low latency fiber and wireless networks to connect New York, London, and that exchange in Dublin to try to get the trading servers as close as possible to the crypto exchange. That was a hugely exciting project for me. I was really looking forward to see the huge impact we would have. A few months later, they traded on it. Turns out almost no impact. I'm like, what is going on? I thought this was going to be amazing. And they said, no, the trading execution times are so slow that, an extra few milliseconds of latency optimization aren't really helping us. Go away and come back later when it matters. That's 2018. So with tears in my eyes, I walked off into the sunset and waiting for this to come back around. And it did. It came back around just last year when I got the call and said, we're ready. There are DEXs, there are centralized exchanges, there are validators running in data centers. There are data centers with huge amounts of validators connected to them. And we now see the traffic, we see the geography, we see how this thing can be optimized. And I said, that's what I want to do. And I released myself from everything else, and I dumped in head first. And that's how I got here and met Andrew one of the very first days, in that whole process, and then met you shortly thereafter. And that's kind of how I got here. I'd love to rehear Andrew's story and your story as well.
So, having spent 15 years in the HFT world building infrastructure, turns out it's hard work, and I was looking for a change in general. And so, as I was sort of exiting my firm, this opportunity presented itself, and Mateo and I, very cliche, met at a bar, and he explained the problem. And it's fascinating, right? To me, I was looking forward to maybe a break, but the way that the problem was described is a network engineer's dream. So you have this problem where transactions are coming into a computer for a couple of seconds and then moving the fire hose over to another computer that could be halfway around the world, and it's doing that every 2 seconds. And to try to reason about that in that moment of time, it was so exciting. I mean, what a different problem space to be working in. Although very different, still drawing on my own experience building custom solutions and building high performance networks. It was sort of a serendipitous moment for me. I said, yes, absolutely, I want to be involved in this. Let's go do it.
And that's kind of where the hook to Austin came in, because little did any of us know, Andrew had been building the first network that is today the backbone of DoubleZero since summer of 2021. So this seems like a new project, and it is. However, the infrastructure has been in development for a few years, which is great, because that's what we need more of in crypto, is people that build first and talk next. So, a lot of execution, a lot of real infrastructure was already in the ground, and we came here to build the project. Why? Because the new FireDancer client for Solana and new next generation clients for many blockchains demand very high performance infrastructure underneath them. In order to meet promises like 1 million transactions per second, you really need to have good stuff downstairs. And so Austin had been interacting with FireDancer, and I think that's sort of where you came in as well.
Yeah, I mean, it's sort of interesting because I get asked this question a lot. Is like, oh, when did you first sort of realize there was an opportunity here to go build something like DoubleZero? And there's no real one one where it was like, oh, this is it. This is the idea. It's kind of like slowly boiling a frog, right? And then eventually you just don't hop out and you realize, oh, I guess we're going and doing this company. Because, so a lot of the original work when I first joined Solana Labs in the very end of 2020 was really focused on application layer development, right? It was doing some of the early work on creating stake pools, working with a bunch of engineers on Metaplex, these sorts of things that were core primitives to what developers now build on top of Solana. But a lot of thought was not given to the connectivity layer, right? A lot of what the software engineers were doing at the time was optimizing and fixing bugs and increasing performance all around how things ran sort of on top of the network, you might say. And the FireDancer project sort of kicked off, sort of 2022 timeline. And this was really a goal of saying, what would it take to get Solana from 10,000 transactions per second to 50,000, 100,000, or 500,000, 1 million transactions per second. And there's been a ton of work by the teams at Anza as well to sort of build towards this vision. But one of the things that I kept, as I was kind of going to these technical meetings and listening to folks talk about it, the bottlenecks that kept coming up were not actually on the compute side. I think for a long time, people in the crypto industry sort of assumed the compute was the bottleneck, right? It was how good can we write code? How fast can we get zero knowledge provers to work? But that really wasn't the conversation that was coming from the Firedancer engineering team. It was that we know how to build high performant code. We do this for, high frequency trading systems all the time. And yeah, it's very different in a validator than it is in the trading execution system. But fundamentally, we know how to do things quickly. The problem was on the networking side. And, I'd be having these sort of side conversations with folks being like, we could build a validator client that can do 1 million transactions per second, but I don't know how we get 1,600 nodes, let alone 3,500 nodes when you include all the RPCs, to be able to have synchronized state with 400 millisecond blocks and be able to run at these kinds of data rates. And so I think it might have been Kevin Bowers who first said, like, hey, there's these two guys that I used to work with one of them, and they're working on this project. You should talk to them and see if this is interesting to you. And we got connected, and so the rest is history now.
Yeah, and I think throughout this whole conversation, we keep referring to high performance networks. And one of the things that's really fun to do is to understand how the internet works. And so that was one of the first things that you and I were talked about is what's the problem, right? What are we trying to solve with this thing?
Yeah, I mean, before we even get into the problem, I think one of the things I run into a lot, and I used to very much fall into this world, is sort of like the magical thinking of networking. That there are all of these types of systems out there, and the internet gets faster and faster every year. There's basically unlimited bandwidth and plenty of bandwidth. But also, software engineers, the kind who work on blockchain, don't think much about hardware. If they think about hardware, they think about, do I have the right CPU to do this, piece of acceleration? Do I have enough RAM in my system? Is my NVMe fast enough? It's not, where am I in the world? What network backbone am I connected to? What are the paths that my packets are physically taking on the undersea cables to get to a different continent? So you two both started off talking about, careers in early telecom and building physical infrastructure for the internet or tying in a data center to the internet. Starting off with a maybe deceptively simple question, but what physically is the internet?
Go for it, Mateo. This is right up your alley.
All right. Well, I'll start off just high level because, the internet is a general purpose network. And Andrew said something very interesting in his initial description of what he built in his career, and they were all purpose-built networks. So what's the difference between purpose-built and general purpose? One big aspect of it is that the internet is built for geographic coverage, to be covering all of the different geographies around the world. But private networks and purpose-built networks are built for where they need to go. They're not built to cover an area. They're built to connect cities, to connect data centers with straight lines. And so the way that the internet evolved is that all of the different ISPs decided that they would peer with each other. And that is something that is a little bit like the hot potato syndrome, because the packets come through these interconnected networks. And we're going to ask Andrew to describe a little more deeply how BGP and IGP work. But in general, they're going to come through these networks and they're going to get routed based on a bunch of criteria that is not related to purpose-built performance. It's related to a whole bunch of other attributes, including political issues, countries that they don't want to go through in order to get to third countries, all kinds of alliances. There are fights, which I'll go into in a minute, about between ISPs that create ridiculous routing. And so the internet basically is sort of like this big best effort collection of a multitude of networks with a somewhat random criteria that routes packets through them. And it's sort of like driving your car down a highway full of potholes and then having to go off the highway because it's there's a big crack in it and go on a side road and then come back on the highway. It's really inefficient to do it that way. You need to build a Formula One track for your Formula One car to drive on, and that's that's sort of the high level. But I'd love to hear from Andrew once again. I love it every time I hear it, sort of how the BGP routing works and the IGP routing works. And you'll be able to, I'll give you some analogies to help understand it as we go through.
Yeah. So at the end of the day, one of the most fundamental parts of the internet is understanding what an autonomous system is. And so an AS, or an autonomous system, is a network that is centrally owned and operated by one party. So it could be a carrier, it could be a large enterprise, but at the end of the day, it's under common management, common ownership. Within the autonomous system, the business rules that the owner of that network applies can be different from one AS to another AS. But when your packet, as an internet user, when your packet arrives at, say, your the ISP who you pay money to, the first thing that that ISP's routing table is going to look for is the shortest number or the least number of AS hops to take to the destination that you're trying to reach, right? But not all AS hops are created.
The fewest number of of independently owned companies it has to go through.
That's right. Yeah. So they look at, we call this the AS path length. So it's going to be if your ISP is directly connected to the ISP that you're trying to reach, or that holds that IP address that you're trying to reach, then it's only going to be one AS hop away. But if it's on the other side of the globe, perhaps your ISP in your local neighborhood needs to get to a tier 1 ISP that has a global network and peers with all of the so-called tier 1 ISPs to reach ultimately that end destination. And this, on the surface, is actually pretty efficient. It's basically like, we call this a path vector routing protocol. So you're using the AS path length as the primary metric to decide where to route your traffic. But where it gets interesting is if the economic incentives inside of any one of those ASNs is such that they want to get rid of your packet off their network for whatever reason, these are the situations that Mateo alluded to where routing starts to be inefficient. So they might want to enter their network in Chicago and get you off the network in Denver, even if they have a link all the way to Tokyo, for example. And in doing so, they create this sort of back and forth circuitous path for your packet to take to reach its destination. Now, if you think about like the owners of the ASNs, they want things to route efficiently, right? But they also don't want to spend money. So their incentive is their incentives are a little perverse from a high performance perspective, because they don't ultimately care about the end-to-end performance of any given flow. They just care that they're not dropping packets and that they're spending the least amount of money to provide that reachability. So that's sort of the basics of internet routing.
Right. And so every time you've got a packet coming out of one validator on the Solana that has to go from Amsterdam to Tokyo, it's quite possible, as you said, it takes a very efficient routed path there. It's also quite possible it bounces around through a bunch of European countries before kind of getting spit out somewhere and eventually making its way to Tokyo.
That's right. And I think that the hosting providers themselves are trying to do the right thing and build networks to accommodate the user traffic. But I think just the default stance on the internet, there's no real reliability guarantee and no sort of performance check that you can say, yes, my traffic is definitely going to take the most optimal path from Amsterdam to Tokyo.
Yeah, this is kind of like I was getting an airplane ticket for my daughter, and she needed to go from South America to Australia. And we wanted to do it on the One World Alliance. And so the only way to do that was to go from South America to Dallas on American Airlines, because Dallas was the only place that American Airlines connected with Qantas, who's part of the One World Alliance. And so you would go South America, Dallas, Australia, which is the most inefficient route that you could possibly take to get to that destination. But it was related to the agreement between those two airlines. And the same thing happens on the internet, and it is ridiculous. There are fights, de-peering, disputes. I wrote some down here just to see how ridiculous it is. The current disputes that are out there that we have to deal with today are BT doesn't peer with anyone in the UK. So Cogent routes to Ireland via New York and Tata routes via London. Cogent and Lumen peer with Deutsche Telekom outside of Frankfurt, creating extra latency for German bound traffic. NTT and Tata are in a dispute with Cogent and have de-peered in Asia, so they route traffic through the US intra-Asia. NTT and Aurelia have de-peered in Europe, so Nordics traffic goes through the US to get to Europe. Like, these types of things are absolutely unacceptable in high performance networks. It makes a network engineer, it gives them the shivers. There's no way that you can route efficiently and have good performance with things bouncing back and forth across the world. So, that's really what the problem is right now for a lot of blockchain networks and a lot of high performance applications that try to use the internet for routing.
So I want to pivot now into the DoubleZero protocol and the physical network that DoubleZero is getting built out and contributed by independent contributors. So I guess, Andrew, I want to kind of start with you today. Like, if you were to describe the DoubleZero network as it relates to either like high frequency trading networks that you've worked on and built before, or the public internet, like, what are the similarities and what are the differences?
Yeah, great question. So I think the similarities between DoubleZero and the internet is that we have a collection of independently owned and operated networks, right? A community of people who are or organizations who are going to contribute bandwidth with a mind to create a unified network. But it's very different than the internet because we're going to provide an orchestration layer to appear as if we are one autonomous system. And so we just talked about the benefits of or the way the internet routes. If you think of DoubleZero as a single autonomous system, we can make guarantees and care about traffic flows, right? And so I think that we get the best of both worlds. You have the decentralization of the internet combined with the experience of a private network that HFTs and other enterprises that care deeply about network performance enjoy.
And what does that kind of mean in practical terms? Like, what are the characteristics of a like high performance private network or a network like DoubleZero compared to the public internet, if you're talking about some of these long haul, traffic hops and routes that packets are trying to take?
Sure. So a purpose-built network, first and foremost, you start with where does the network need to exist? And so when we look at building a network for the blockchain community, well, it's very public where the validator nodes are sitting, and that's the network that we're trying to build. So we're first and foremost going to bring the network into locations that we know we want to connect together. So we're going to go to geographies that for a proof of stake blockchain like Solana, we would identify where the stake exists and make sure that we have a point of presence in that geography. I think the next piece is of a high performance network is the links are not so noisy as the internet, right? There aren't going to be cat videos going around the DoubleZero network, right? This is a network that's built for building consensus, for voting, for taking transactions in, and we sort of still have the global internet, which is a wonderful service, so that we can do other things on that network. So yeah, that's I think the basics.
And I'd like to kind of turn that into a couple analogies because it's interesting to think about in real life what this type of thing would look like. So if you look back in Web 2, networks are controlled by centralized hardware. So centralized hardware controls the software. But in Web 3, it's the other way around. Decentralized software controls the hardware. And so it would be ludicrous to use a network that is not controlled by software to support Web3. And so like if you think about your house as a node on the blockchain and you say, well, how do I get from my house to the closest highway? Well, I have to go down a side street and then I have to turn right and then I go on a larger street and then I end up getting to the highway. But what if you built your house right on the highway? Like the Tom Petty song Free Falling, where there's a freeway running through his yard, right? It's like the freeway is running right through your front door and going out your back door. Now we're talking. Now we're in a data center and now we're sitting right on the fiber. But it has to go through the front door and go out the back door. And that's how the internet works. There's no other options. It's nailed up. It goes through the front door, it goes out the back door. How do you get to your neighbor's house? Well, I open a window and I can get out to my neighbor's house. What if your whole house was built of doors and windows and you could open them all and go wherever you want? Well, that's analogous to software-defined network because I've got a controller sitting above the network that allows traffic to be routed through any door, any window, on any fiber pair that's connected efficiently to the place that I'm going, the data center or the city that I'm going to. And so we're building a network like this. And the beauty of it is that you can combine business rules or requirements from users with routing protocols and routing decisions. And so the network that Andrew and his team are engineering is a very advanced software-defined network that will allow traffic to flow where it needs to flow in the most efficient way. And that has never been done before in a permissionless way and using private networks that are purpose-built and making those networks open and available for anybody to use without long-term commitments, without huge CapEx investments like most of these networks usually require.
Yeah, Andrew, I want to talk a little bit about how this actually works from like both a validator and let's say an RPC's perspective. So I think, most people are familiar with like validators are servers. They are run in data centers. They have Ethernet jacks or something similar on the back of them that's plugged into a network. And that network, through enough switches inside the data center, eventually connects to the public internet. And that's how, if you go on to validators.app or Solana Beach or any Explorer, you can look up and say, like, where is the Helios validator located? You can get an IP address. It'll tell you about where in the world it's located. And at any given moment, it's talking to a bunch of other validators and voting and building blocks and doing all the stuff that we know and love on blockchains. That all happens today over the public internet. So when you're introducing DoubleZero into the mix, like, is that another network jack in the back of the validator that's plugged into something other than the internet? Like, if I'm a validator operator, what's it like when I'm running my Solana mainnet validator on DoubleZero as opposed to running it on, the internet?
Yeah. So initially, when you build a network, the first thing you want to do is make it easy to connect to. And so it's not easy to build a network that requires additional hardware. And so the DoubleZero network aims to sort of thread the needle of creating a high performance experience without creating a dedicated physical connection to the device, to the DoubleZero network. So what we've done is we've shipped a software stack that allows any computer on the internet, any running the Linux operating system, to establish a virtual interface to the closest DoubleZero node. So if you take the example of a bare metal hosting provider offering services in Frankfurt, Germany, the computer is physically located in a sort of a carrier-neutral facility that's maybe owned by Equinix or Digital Realty or any number of these data center owners. And then the hosting provider leases a cage and space and power and racks their servers up and connects it up to the internet, as you say. The only thing that the end user, the validator operator, needs to do is install the DoubleZero command line interface and author a smart contract using that command line tool to create this virtual interface that will connect that computer using the public internet to the nearest DoubleZero node. Now, we just talked about how the internet isn't a high performance network. However, the internet, when it's kept to short distances, is actually quite a performant network. And so if in this example where the hosting provider's in Frankfurt, if the DoubleZero network has a switching device also in Frankfurt in the same metro area, or even ideally in the same building, then you're still only a few switches away. So it sort of negates the poor performance attributes of the internet and allows you to have no additional hardware costs in order to connect and onboard onto DoubleZero.
And then from that, like if you're, I've installed this software package on my validator. It's created a virtual tunnel interface connecting into one of these DoubleZero switches that's run by some independent contributor who's decided to contribute a piece of fiber that ends in Frankfurt. Where does it go from there? Like we're then connecting into pieces of glass that run hundreds of miles. Like what is like, I think a lot of people, when they sort of think about this stuff, they're like, yeah, okay, the internet's a series of pipes, but like, what does that mean in the case of something like DoubleZero?
Yes, it is all just tubes. That's all we're doing here at DoubleZero. So the physical DoubleZero device is a 1 rack unit high device. So it's an inch and a quarter, I think, is a rack unit. So that's how high the device is. It has 48 physical ports on it that all look like the network interface you mentioned on the back of a typical computer. And so the device itself, the switch itself, has an internet connection because that's how the validator packet is getting onto the device in the first place. But then on some of the other physical interfaces on this switch is where we attach to the network contributors, the community of DoubleZero contributors who are offering access to their private network. And so this is the key. What we do is we literally do have a physical cable connected to that network contributor's network. And from there, it's riding a very direct path that will sometimes be a wavelength service, will sometimes be a packet-based service, but across that carrier's network directly to a destination city. So in the case we've used before of Amsterdam to Tokyo, the network might take a hop from Amsterdam to New York to Los Angeles to Tokyo. Right. Whereas, as Mateo mentioned earlier, if you just did that over the public internet, you might be bouncing all around Europe and to the US and back to Europe and then over to Asia finally. And so, yes, it does take a very direct path, and it's certainly going over physical fiber optic cabling, traveling under, these cables are, Mateo made a career out of laying these cables under the sea. So, it's physical fiber optic cable infrastructure.
Yeah, and it's getting as close as possible to the limits of the laws of physics, basically. So if you think about what's physically possible, we want to get as close to that as we can. And that's why one of our core values is to have sort of an insatiable hunger for knowing where. A lot of people want to know why things happen, but we want to know where things are. Because that's what's going to allow us to design physical infrastructure to get from point A to point B as close to the limits of the laws of physics as possible.
I mean, I think this is the part that a lot of folks are like, okay, so we have packets traveling over a piece of glass under the ocean, and then they pop up, let's say in Tokyo. Then what? So we have a piece of fiber that's coming out of a big cable through a hole in the ground. It comes into a data center, and then there's another DoubleZero switch on the end of it. Like I think, like it almost seems too simple. That it's like when you're a kid and you have a bunch of tubes and cups and you're like talking to your friends over 20 feet or something like that. Like, and then at the other end, the validators are also connected in via these software tunnels, and you just eventually grow this map and grow this, for lack of a better term, spider web network larger and larger, and you're connected into all the data centers that validators are operating under. Is that basically the vision?
Yeah, simplicity is beauty. I mean, private networks are much more simple to build than things like the public internet, because you just define from where to where and you build it. The hard part of what we're doing is turning these private purpose-built networks into a cohesive, open, permissionless public network. That's really the challenge. But you're completely right. It's simple. It's Lego blocks. It's just putting the pieces together, plugging it in the most efficient way possible, just like all high performance technology has been doing for decades, including the cloud, finance, artificial intelligence. Any high performance technology, demanding technology, has these purpose built networks under them. So yeah, it's as easy as plugging those things together. The hard part
Yeah.
is plugging them all together with each other and creating a single unified open network.
Oh, yeah. I mean, a fusion reactor is very simple in theory. The sun does it every day, but the realities are a little bit more challenging. So Andrew, I want to talk a little bit then about the hard part here that Mateo just started talking about. The idea that this is not a network that's run by one central company with a big ops center somewhere and a bunch of staff and employees that are, monitoring network connections. This is a network that is living up to the principles of blockchain and being run by multiple independent contributors. How do you mesh that kind of messy human reality of multiple people involved with the technology and the desires and the requirements to run a high performance network that appears to the server operating on it as one heterogeneous network?
Yeah, great question. So we started, as I mentioned, with the user provisioning part of the problem. So whereas if you want to connect to a network in Frankfurt, Germany, you might have to contact one ISP on the internet that's different than the ISP you would use if you were in Los Angeles, California. So what we've attempted to do is leverage the beauty of smart contracts. And so if you define the network on the blockchain itself, so that the data structures that define where the DoubleZero devices are physically, what their IP addresses are, and all of the properties that are needed to know about the endpoints of the network, then the users already have this sort of regardless of who owns the node in Los Angeles and who owns the network and DoubleZero node in Frankfurt, the provisioning system is the same because the providers have defined what they're providing on the blockchain. So I think the first thing that we're doing is making it so that you normalize the way that a contract gets built and a user gets provisioned. The next phase of the decentralization effort is really around the control plane itself. So when you have independently owned and operated networks like in the public internet, there is no common control plane across them, as we mentioned earlier. And so the idea is that the controller is a software package itself that runs on the DoubleZero device and has knowledge of the entire network because the network is actually physically connected together. All of the contributors have connections to an exchange point that we call a DoubleZero exchange that creates the appearance of a contiguous physical network. And because we have protocols running inside the network that the device has total awareness of the network graph or the topology, the physical topology of the network, the software now can reason about the entirety of the network and make routing choices based on rules that we define to ensure that the traffic is routed as effectively as we want or as ineffectively as we want. Because in some cases, you might want to use the DoubleZero network in a way where your path you don't care about a latency property perhaps, and maybe you just want kind of reachability and high bandwidth, and you don't care so much about the path that it takes, right? We can also back out and operate in that mode.
Right. So for systems where latency is very important, there's optimizations capable for that. But if there's applications using DoubleZero that require moving lots of data, but 50 milliseconds one way or another is not going to matter to them, you can optimize for that as well.
That's right. And I think that there's often a tension between bandwidth and latency where the fastest links from a latency perspective often have scarcity of bandwidth. And so we can do both. So if you want temporarily to nail up a 100 gig connection between two regions of the world, you can do that with DoubleZero. I think about a use case where someone wants to move a bunch of data, maybe it's a CDN, wants to move a bunch of data from one central point out to many different places. It's not a real-time operation, so it's not maybe a trading transaction, but they want this bandwidth and they only need it for a short amount of time. They could have a smart contract, and then they could end that smart contract and get the benefits of sort of high performance networking as a pure utility.
So what will the DoubleZero network provide for folks who are designing the architecture of blockchains, looking at raising protocol limits, all these sorts of performance optimizations and capacity increases on the software side? If a validator or a validator set is operating on the DoubleZero network, what are those software engineers who are building blockchains able to do that they can't do on the public internet?
I'm going to take the high level of this because I think there's a business aspect to it, and I'd love Andrew to fill in the tech part. But the key here, as I've said before, is combining the business needs with the ability of a software-defined networking to run the traffic through the network however a use case needs. And so we've got a bunch of different options that you do in traditional high-performance networking, like multicast is one of those.
Could you define what multicast is?
Sure. So multicast is something that's a sort of a dark art of networking, I would say. It's used widely in finance because you have this classic problem of one piece of information that needs to go to many consumers. In finance, it's usually the pricing information of a security. So maybe you want to know the last price that a stock was bought and sold at. And the exchanges need to disseminate that information to all of the participants at the exchange. But you don't want one computer to have to send to the thousands of participants, right? Because if it just did that serially, not only would it take forever, because they would have to be done one after another, you would need a very high-powered computer, and you'd be like a massively inefficient use of bandwidth. So multicast is a protocol that allows a computer to send a piece of information or a packet one time, and then computers that are interested in joining that so-called multicast group, they have a protocol to express their interest in receiving that information. So multicast is really appealing in the blockchain use case because a proof of stake blockchain wants to build consensus, and in order to do that, as blocks are produced, the entirety of the cluster needs to see the same information. And so great lengths and great development efforts have been done to date to replicate in a non-multicast network the concept of multicast. So things like Merkle trees are used to unicast a message to one computer and then have that one computer unicast it 200 times to some set of validators, and then the next 200 to the next 200, right? And that's all a slow software process, but with no knowledge of the underlying geography of how that tree, which is effectively the structure that it's built, with no knowledge of the geography of that tree. In networking, the multicast tree is built on the shortest path. So the tree is automatically the most efficient, shortest path tree. So if you're in Amsterdam and you send a multicast packet into the DoubleZero network eventually, that packet will find its way to all the other computers that are connected to the DoubleZero network over the shortest path, not through this software process of maybe sending to a root node that's in Tokyo and then back to New York and then over to Los Angeles and so on. So it would always take the shortest path.
Yeah, I think this is so emblematic of like the thinking of network engineers versus like software engineers, because what you're describing is Turbine, right? That's the way Turbine works, that one packet is sent out and then it's sent out 200 times and 200 times again, and eventually it gets to all the nodes. But Turbine does packet distribution by stake weight. And the assumption there is, well, if you have 5% of the stake, it's much more likely you're building the next block than if you have 1% of the stake. So therefore, we should prioritize getting you the data more quickly. Although in reality, building the tree that way may result in getting them data more slowly just because of geographic distribution.
That's exactly right.
Yeah, it's one of these really interesting pieces I love digging into, just like how the paradigms of different parts of what we all sort of identify as computer engineering think about the same types of problems in really different ways.
Now, it's important to say that in a multicast system, while it is the most efficient way to distribute the data, you also need protection mechanisms against lost data. Because one of the properties of multicast is, there is no, if a packet's dropped, there's no replay mechanism. So you have to build that sort of error recovery or drop packet recovery into the protocol. Fortunately, Solana has done that already with the turbine system. So I think a network like Solana is ripe for using multicast.
And you can't run multicast on the public internet.
Yeah, that's right. One of the big challenges of running a multicast network is it's often not interoperable across these autonomous systems. So while one autonomous system may offer some sort of multicast service within its own AS, it's very infrequent that you'll find services that can traverse multiple ASs. So it's generally not accepted. It's not something that a hosting provider would offer access to. Multicast is just generally not allowed when you're connected to a typical ISP.
And so what are some of the other characteristics of DoubleZero that make it attractive for like high performance blockchains and other types of distributed systems?
Well, I think one thing that comes to mind is the use of hardware acceleration in the network. So one of the properties of DoubleZero is that we have user programmable FPGA devices inside the DoubleZero switches. Now, what's an FPGA? An FPGA is effectively a piece of hardware that you can program to operate at line rate and look at network traffic as it's traversing the switching infrastructure. So that all sounds fine. Why would you want to do that? Well, you may want to inspect the packet to see if it has a valid signature on it. And you may want to, in the case of a blockchain network, you may want to ensure that transactions are only arriving at validator nodes one time. So you reduce the amount of spam transactions that the validators themselves have to handle. So these are applications that we are intending to put at the edges of the DoubleZero network to use the network to offload some of the capabilities or compute needs of the validators themselves.
And so how are FPGAs used today in networking? I understand they're pretty common in some high performance trading setups.
Yeah, I've seen the evolution of the use of FPGAs in previously software only stacks and sort of play out in two different ways. NASDAQ, the stock market, decided to offer an FPGA-based market data feed, their itch feed, which distributes all of the price information of the securities being traded on NASDAQ. And the reason that they did this was the performance of a publisher in hardware is far superior to anything that you would see from a software-only stack. Likewise, on the HFT side, trading companies use FPGAs to guarantee performance and avoid buffering that occurs when you bring a packet into a software networking stack. So you might see that an FPGA is used as a feed handler, where that NASDAQ FPGA publisher is sending the packet, while on the trading system side, they're taking the A copy of that from the exchange, the B copy of that from the exchange that are being sent twice for redundancy. They're arbitrating the A and B, the first packet, and only sending out the next, one version of that into the internal network to trade on. And so these applications are really nice bump in the wire style applications where you can operate at line rate and have effectively no queuing delay because they're operating in a cut through mode.
Yeah, all this stuff is very interesting to me because Andrew and I have been working in this world for quite some time. But when we listen to blockchain people talk about these things, they talk about things like decentralized NASDAQ and how to compete with centralized systems. But at the end of the day, it's just a matter of putting all those same components in place on the blockchain. And I was going through it with a trader the other day, each piece of it, and saying, well, the order's placed, a matching or execution engine executes the trade by looking up the symbols in an order book. The pricing crosses, they execute. The trade gets pulled into a market data feed, which is multicasted back out to the market, combined with market news feeds, and then a circle comes back input to traders and they trade on it. That's all done in centralized locations, but multiple centralized locations throughout the world. So the geographic distribution is there, but what's not there is that you can't do it from anywhere. You have to always go somewhere in order to place a trade in a matching engine. And so the blockchain community seems to be talking a lot about how to have this be completely distributed. And neither Andrew nor I can imagine a world where you could achieve that on the public internet or on any network that wasn't custom built to be able to do all of those things, not only with low latency, but with all of the components needed for those transactions to work, to be distributed and decentralized throughout the world. So everything that Andrew just talked about, about how it works in the traditional finance world is what the blockchain community and now us as part of it need to think about and work on over the coming months and years to make that whole thing work.
Yeah. So before we wrap up today, you two come from high performance networking background, telco, buttoned up TradFi. How has the transition into crypto been? What surprised you? What's been sort of more confusing than you expected? Like it's a big cultural change. The same thing I'm going through, learning high performance networking. You guys are going through learning this crazy world of crypto.
Yeah, it's really fun. I'm having a blast. Starting with my T-shirt. So IBRL is increased bandwidth, reduced latency, and it's kind of become a theme for everyone who's interested in projects like DoubleZero. And I just had this shirt made up on Amazon, quick and dirty. Anyone can do it. And I was telling the story on a call with a bunch of blockchain validators, and the community came up with the word open source swag and said, yeah, it's anyone can do it. You just get IBRL printed on a T-shirt, and that type of thing is really cool. It just happens. Everyone's supportive, and there's other things out there that I've seen. I think neutrinos is a meme almost in blockchain. Everyone talks about neutrinos as a joke. They're not a joke to me. I take them very seriously because that's the next frontier of data networking. For those who don't know, neutrinos are subatomic particles that can travel through the Earth through matter. And back in 2012, the first neutrino message was sent 1 kilometer through the Earth between two locations near Chicago. I think there's more to be done there. I think that it would be great if we started a research hub to pull together researchers on neutrino and use that wonderful sort of crypto blockchain community attitude to help advance science and help advance networking. And I really feel like this community is open to ideas like that. And it's really the first time I've been in an environment where you can sort of throw ideas out and people gather around. If they're good ideas, they gather around and help you achieve those goals. So I'm having a blast. I don't know about you, Andrew.
Yeah, for sure. I think the first thing that comes to mind for me is being able to talk about my work in the open for the first time in a very long time. So, there's quite a lot of, secrecy around how the high frequency trading systems are built and whatnot. And I think that we were able to work out in the open is a wonderful thing. I found the community to be incredibly energetic, and not to say that that's not the case elsewhere, but energetic, open, just wanting to make it work, passionate about the notion of decentralization. I have a renewed energy in my career that I can't describe adequately, but I'm more engaged in my work than I've been in a very long time, and very much enjoying my entry into the Web3 space.
Awesome. Well, I think we have to leave it at there today, but Mateo, Andrew, IBRL.
IBRL.
IBRL.